Hi! Today we will see how we can compute the Laplace transform of piecewise functions. So functions that are non-continuous and maybe they are non-continuous, and how we can compute the Laplace transform in that case. It will be very handy to use the Heaviside function. Remember that the Heaviside function is basically a unitary step at a given point A. If we write just ut, we are assuming that the step is at the origin when t equals 0. And when we write u sub at, means that the step is at this point A. Okay? We will see that this Heaviside function will help us to rewrite any piecewise function in a specific manner that it will be very easy then to compute its Laplace transform. So let me go to this slide where we state that any function defined in a piecewise manner that you can think about, it will always be possible to write it down as a linear combination of Heaviside functions. Let's try to do that, okay? Here, we define a function ft that is a piecewise function. You see, we define that prior to the value a, the f of t is defined by f1 between, and it is plotted here, then between a and b, the function ft is given by f2t, and then after b, the function ft is defined by the expression f3 of t, and here you have an example on how this ft function looks like. At the beginning, it looks like f1, then it switches to the definition f2, and finally it switches to the definition f3. In general, you can have many cases, but there are basically these three cases. That is when t is smaller than a given value, when t is between two values, or when t is bigger than a given value up to infinity. So we will work with this example because it really takes into account all the possible cases. So let's try to do it by hand. Let's go to the blackboard and let's see if we can really write down this function ft. Let's see if we can write it down like a linear combination of Heaviside functions, okay? What's the meaning of that? The meaning of a linear combination is that I'm saying that I should be able to write down f of t in a single line where maybe there will appear some Heaviside functions, okay? And what I'm going to do is I'm writing this idea. Let's say I will use f1 on f1t when I am in the initial interval where t is smaller than a. What I'm writing here is what I call a switch-on, switch-off function. This function is going to be 0 when I'm not in this case, and it's going to be 1 when I'm in this case. So maybe it's better to write it in a different way. So this switching function is going to be 1 when t is smaller than a, and 0 otherwise. Okay? So this is a switch-on, switch-off function that will switch on, it will be 1 when I'm at this case, and then the function will have this value. Then I will have f2, which is accompanying switch-on, switch-off function, and the same idea for f3, which also will have this switch-on, switch-off function. Okay? So that's the main idea. Let me see if I can move this a little bit here. Okay. So let's see if we can derive who are these switching functions, okay? First case, well, first of all, do you really understand that if these are switching functions, here, for example, this switching function is going to be 1 when I'm at the f2 case. So if t belongs between a and b, it will be 1 and it will be 0 otherwise, because this is the switching function related to f2. And in the case of f3, this switching function here is a switch on, switch off case, yeah? If I'm at case related to F3, if I'm at this case, the switch should go to on, yeah? 1. So that's when T is greater than B and 0 otherwise. In this way, when I'm at this case, for example, it will happen that this switching function will be 1, but this will be 0 and this will be 0, and F1 will remain there. However, if I'm in this case, between A and B, this switching function is going to be 0. And also this switching function is going to be 0. But this one is going to be 1. So F2 will remain there. The same for F3. When T is greater than B, this switch function will be 0. This function will be 0. But this one is going to be 1. So in that case, Ft is going to be equal to F3. So it's a very simple way to think about this. And now the only thing we must accomplish is to write down these switching functions using Heaviside functions, okay, using linear combinations of Heaviside functions. But that's pretty easy. First one, let's write as linear combinations of Heaviside functions. The first one, let's use colors. This first switching function, I want a function that is, or maybe it's better to do this in another color and then switch to the orange. So let's say we plot first the axis and then we plot in orange this switching function. Okay, now the switching function should be 1 when T is smaller than A. So let's say this is A. T smaller than A should be equal to 1. And then it should be 0 everywhere else. Okay, this looks a lot to the Heaviside function, but it's not exactly equal to the Heaviside function because the Heaviside function looks like this. The Heaviside function, UAT, remember that is in a step that goes, it's in a step that goes up, not down. So UA is a function that is 0, and when it comes to this point, it switches to 1. So somehow it's like the opposite, yeah? How can we write down the orange function from the red function? What do you think about this? 1 minus UAT. If I use the constant function 1 and I subtract the red function, which is UA, 1 minus 0 is going to be 1. Oh, that's the orange I want. Great. What about after A? Okay, after point A, 1 minus 0, 1 minus 1, which is the value of UA after A, is 0. So I get the orange curve I want. So 1 minus UA is this orange function I plotted here. So this switching function is already constructed, and it's a linear combination of Heaviside functions. In fact, this one, UA. Let's go now to the second switching function. For the second switching function, it is important. Let's change the colors. Let's say now we will do it in green color. Now I want to plot a green function that looks like this. Let's say this is A, let's say this is B, and this function is 1 between A and B, but it's 0 after and before those values, okay? Okay, how can we write this function just using Heaviside functions? Of course, here it will be helpful to plot UA and UB. UA is 0 here, and then it switches to 1. And UB is 0 here, and then it switches to 1. That's UB. Okay, so here it is 0 also, up to B. Okay. How can we construct this type of Mario Bros platform? Okay, how can we construct this? Well, what if we try with one minus the other? For example, UB minus UA, or UA minus UB. Let's see which one works. UA, let's try with UA minus UB. Let's see what happens. UA minus UB here. Well, here the red and the brown functions are both 0. So when I subtract them, I will get 0, which is what I want, because what I want is the green color. Okay, 0 minus 0 is 0. Great. What about between A and B? Between A and B, UA, the red curve, is 1, and the brown is 0. 1 minus 0 is 1. Oh, that's what I want. It's the green curve here has value 1. What after B? What happens after B? Well, after B, the red and the brown, UA and UB, they are both equal to 1. So when I subtract them, I get 0. Oh, that's what I want, 0. The green curve here is equal to 0. So in this way, I managed to construct the switching function for F2. Let's go to the last switching function. Let me try to move this a little bit here. Okay. Now let's see if we can construct the last switching function. In this case, what I want is a function that is 1 when t is greater than b. Okay, so let's say this is b, and I want a function that is 1 here, and it's 0 otherwise. So it's 0 otherwise, okay? So that's pretty simple. What's this function? It's a function that is 0 before b, and then it's 1 after b. This is exactly the definition of UB. So this switching function is UB. So we proved that it's very simple to write any function defined in a piecewise manner, like this one. It is very simple to rewrite it as a linear combination of Heaviside. And here we have the final way on how to do that. And we have the three cases that we can find. First case, when t belongs to minus infinity a, we solve that with this type of switching function. The other cases, we can have a lot of these cases when t is between two values, but all those cases will be treated like this. Of course, as many different piecewise parts the function has, more Heaviside functions we will use. At each point where we have a change in the definition, we will have a Heaviside function there that we will have to use. And finally, the last case, when t goes from b to up to infinity, then we will use this type of switching function. So that's what I wanted to explain about how to compute, how to rewrite a function that is given in a piecewise manner in such a way that you can write it in a single line. You see here you have cases. Here you written f of t in a single line of code, just one line. How? By using the Heaviside functions. So that's it for today. Thank you for watching. Bye bye.